Hi again. It's time to talk convolution kernels. This is a fundamental concept used in image processing, and particularly in creating blurs and sharpening and things like edge detecting and other types of things. So let's just dive into Howler's convolution filter here and take a look at some of the things that are happening here. The default is like an blur effect. And there's also sharpen and edge detect and a few other things in there. Now, what is actually happening when you see all these numbers here? Let's jump over and take a look on the Wikipedia. Or no, I'm not sure where this is, but as you can see here, there's some examples of different kernels. The simple box blur is what we're seeing there, the box filter. And you can see it just has a slightly blurring effect. And then there's this requires a much larger kernel, but there's a Gaussian blur, and that makes them a bit blurrier and a bit better quality blur. Line detection, edge detection, Sobel, which is a type of edge detection that helps eliminate noise from the image as well and gives a better quality edge, a softer edge. Laplacian operator, which is another type of edge detection. It helps find the difference or the edges in an image, the amount of change in an image, and also the Laplacian of Gaussian, which is a combination of two different kernels. One blurs the image, and the other one is an edge detecting, or the Laplacian. Both combined into a single kernel, and this has the effect of first smoothing out the image and then doing the edge detection. And these are some fundamentally very useful image processing concepts. So what is actually happening? If you look at this small kernel here, you see all these 1, 9, 1, 9, 1, 9, 1 divided by 9s. And basically what we do when we're using a image processing kernel, a convolution kernel, is just think of it as the middle. This middle box here is the pixel that we're working on. Yes, we work on all the pixels of the image, but at any one time we're working on a single pixel. And all these other boxes are the neighboring pixels. So if you think about this, all these 1/9, and there are 9 boxes, adds up to 1. That means we're taking the center pixel and we're adding the pixel value of this one here times 1/9, and the pixel value of this one here times 1/9, and the pixel value of this one here times 1/9. All of these values were added together, multiplied by 1/9, equals all the pixels together, averaged together, basically. Another way you could do that is if we went into Howler, we see 1, 1, 1, 1, 1. Well, we're just taking all of the pixels, multiplying them by 1, meaning you're getting the full value. We're summing all those 9 pixels, and then we're dividing that, or in other words, we're averaging all those pixels, dividing that by 9, or the number of boxes. So is that clear? What we've done is basically averaged all of the neighboring pixels plus the pixel we're working on to produce that one pixel. And that averaging effects, that averaging has the effect of blurring the image. I hope that's clear. That's the blur. Now when we do a sharpen, we're doing something slightly different. We're subtracting, let's see, we're subtracting the neighboring pixels, and we're adding the middle pixel times 5. That has the effect of sharpening the image. It accentuates the edges. Let's see, and then another good one is this Laplacian filter, very similar to sharpening. Actually, we're using a 4 instead of a 5. And if I put this offset at 0, we'll see that we're getting the edge detected. And this is intuitive when you think about it. If you wanted to find the difference, mathematically, the difference between two different things, you would subtract one from the other. Say we want to know the difference between 9 and 10, you would subtract 9 from 10, and that would give you 1. Well, if you wanted to know the difference between pixels, you would subtract one pixel from another, or the value of one pixel from another. But if you wanted to know the difference between this middle pixel and all the surrounding pixel, you'd have to give the middle pixel a higher value so that it equals the number of the pixels that you're adding to it. So in this case, we're multiplying a 4, or we're multiplying the middle of that center pixel by 4 to overcome the fact that we're only multiplying these 4 pixels by -1. So if you add up that -1 times 4, that's -4. And then when you add the middle pixel, it evens out. So that is in fact the Laplacian filter. You're finding the difference between the middle pixel and all the surrounding pixels, or in other words, wherever there's an area of great change, you're going to have a higher value than where there's an area or a pixel of small change. I hope that's intuitive, because like if we subtracted 9 from 10, that would be a small change, but if we subtracted 2 from 10, that would be a much bigger change. In the same way here, if we're subtracting pixels that change a lot, we get a bigger value. And as I said before, this offset, all that does is adds a value to a literally a luminance value to the pixel. That lets you adjust what you're seeing. In this case, we set it at 128. That's 1/2 the brightness of the maximum brightness of a pixel. That gives us some light areas and some areas darker than that middle value. And it's just kind of a convenience to help us see the positive and negative values there. So that's convolution kernels. Hope that was somewhat intuitive, and maybe we can talk more about this later. But that's just one little thing in image processing that's fairly you can unify by using this simple trick, or this simple math scheme here. Thanks for watching, and talk to you later.